Started with that. So, without further ado, let's get started with resources beyond Earth. So, before we start, let me remind you, this is something that I want you probably to remind you every class. There's many resources out there in the solar system. Just checking to see, do you see now like the solar system there?
No.
Great, too great.
Don't? Like, did you see that I changed from one slide to another?
No. Oh, it's
There are
great.
slides.
Oh, wait, I gotta share. What am I doing? Let me share. Here. All right. Well, that's why you couldn't see it.
Now we have
Okay, yes.
Now you see it. All right, you see resources beyond Earth, right?
Yep.
All right. So let me start in again with the most important thing that you have to learn from this class, which is that our resource is valued by its utilization. And I want you again to keep this in mind as we are going, I'm going explaining everything during this class. And remember the three important principles. You gotta have a recoverable resource, you have to have the technology to recover it, and you have to have a customer that will demand it. If not, the resource is just, an element of scientific interest or curiosity. So keep that in mind as I go along and explain the various resources in the near solar system. So let's get started where we left last time. Again, this class is going to be about the first part, recoverable resource. Next week we'll move to the next, the technologies. Eventually we'll move to the customers, so you can see the whole thing and then start evaluating, putting it all together in what is called a resource utilization plan, which will be your final project. Okay, so this is what we left it last time. We talked about the intangible resources. These are things that you cannot collect, you cannot mine, you cannot extract. This is vacuum and low gravity in low orbit. There's sunlight that you can use to power spacecraft, but also you can beam them down to Earth in the future. And there is the view from above. That it's important because that gives you pretty much everything that we're doing right now in space in terms of commercial satellites, communications, and weather forecasting. And so, let me just minimize this little thing. Let's see everybody. Okay. And so, in order to get more concrete elements, in order to start figuring out now how we can extract more tangible resources, we're going to have to start now traveling to our nearest destination. That is our moon. And that is just a few, like 360,000 kilometers away from us. And our moon is a place that we landed 50 years ago. And interesting enough, when the astronauts got there, there was not much hope of any reason. In fact, if you look at the recordings from what the second man on the moon said, the moment he stepped out of the lunar lander, the first thing he said, he looked around and he said, "This is magnificent desolation." There was nothing there that there could be of use. There was no oxygen to breathe, no water to drink, no food, no wood, cows, nothing that could be of use to humans. But our view from the moon has changed radically since then. What has happened is that we have sent dozens and dozens of satellites moving around, and they have taken remote sensing. This is the prospecting, finding out what's out there. We also have samples from the moon. We have rocks that have been picked up by the Apollo astronauts during several missions, about 350 kilograms. The Russians also landed a couple of missions and brought back robotically several grams of samples. So those samples and what we have from orbit have been very important to turn what has been magnificent desolation into a place that is full of resources that can be utilized in the future, depending on what it is that we're looking at. But in order to understand more about the resources on the moon, it's important to look at our moon in a closer way, in its geological context. These are the two sides of the moon. Okay, one is the near side, the one that we see every night. You can see here is a bit darker. And then we have the far side, that is erroneously called the dark side of the moon, because Pink Floyd had a song in the 1970s called The Dark Side of the Moon, and there are books about it, and everybody talks about the dark side because we don't see it But in fact, it gets a lot of light. 2 weeks, every side of the moon gets 2 weeks of sunlight and 2 weeks of darkness. But it just so happens that the moon is what's called tidally locked to Earth. So when the moon goes around the Earth, it just, it has one side, and this side is always looking at the Earth. What happens is that one revolution of the moon corresponds to a revolution around the Earth. So that's why you always see one side. We never see the far side of the moon. And that's something that happens with a lot of moons around planets. They're tidally locked. Now, what you see here on the near side, this is where most of the information that we have received are from. This is where the Apollo missions landed. This is where the Russians landed, because they were close to us. We can see and we can communicate. Going to the far side is very difficult because you cannot communicate, you cannot see. But that changed. That changed this January with China. And Rudy, you must be very proud of your country.
Yes.
Because for the first time, we were able to soft land in the far side of the moon. And it happened on this place called the South Pole Aitken Basin. Even without pointing it to you, let me go back. You can see that there's something different there. There's a little bit of a darkness side of that side of the moon, whereas the other one is very bright. This happens to be one of the largest impacts in the solar system. This is where a big impact happened. It broke the crust of the moon, exposed some of the liquid in the mantle, and came out and filled that section. And this is exactly where Chang'e 4 landed in January on a crater called the von Karman crater. On the first meeting that we had, there was a professor that he was coming from the von Karman Institute. And this is a famous German astronaut, but that's German scientist. But this is the name of the crater. And they landed on this very soft spot. And not only landed, they actually put a rover that gave us the very first beautiful panoramic view of the far side of the moon for the first time. They were able to see it, communicate with a satellite on the other side, relay the information, and we got to see it. This is a fantastic achievement that has been very difficult to get for 50 years. And what this has given us is a view of what type of resources could be on the far side. And as you will see, it's a very important spot, probably the best spot on the far side. Let's see why. Well, first of all, if you try to see what resources could be available, let's say, for example, is there any oxygen on the moon? Tell me.
No. There's no atmosphere.
No, right? There's no atmosphere. It's a vacuum. Well, you'll be surprised to know that 45% of the moon is oxygen. Where is that oxygen?
In the soil.
It's in the rock. Yes, in the soil. These rocks on the moon are oxidized. And if you heat them up just a little bit, 600, 700 degrees Celsius, the oxygen will start coming out. So it's locked on the mineral. You have to spend energy. But there's plenty of oxygen all around the moon. Not only that, silicon, that very important element for our semiconductor industry, there's 21% of it. It's all over the place. It's very much like you find the sand of the Earth. It's just a little bit different. We'll see why. But this is where the similarity between the near side and the far side end. For specific elements, you have to concentrate in two important regions that's very easy to see. I mean, the first thing, what is the first difference that you see on these two sides? What's something that attracts immediately? That is different.
The surface?
Color of surface.
Circles of, what else? Something that is very obvious.
Criteria,
The amount of craters.
Something that, what's the difference between the far side and the near side? Anything that stands out?
There's no more craters on the far side.
It looks like craters, right? But it looks darker. It's some people say that it's the man on the moon, a rabbit, something in the near side. It's these dark colors. That's what's called the Maria. And it was called the Maria by Johannes Kepler in the 1600s when he thought that these were seas or oceans. So Maria in Latin is seas. And so he thought, there's some seas or oceans on the moon. And that's that's made out of volcanic material or basaltic material, which means there were craters, and there are craters everywhere. But what happened is that there was volcanic material. This volcanic material inundated or flooded those holes, and it's full of basalt, which you find on Earth. Every time there's an eruption, you find volcanic material that comes from the mantle, the liquid part, and inundated these parts on the moon. and that's why it looks dark. It also looks, as you can see, because it's younger, it came later, you don't see many craters here. You see a few craters, but the rest is extremely cratered. But this is, since it's newer, there's less amount of craters. There was a period in history, and you will see that in another, during the week, in another of the lectures online, how there was a period in which there was the bombardment period. There was a lot of craters. And that's why you see that. The other side, the white part is called the Terra, or the highlands. This is the primordial crust of the moon, the most ancient material on the moon that has not been flooded by volcanic material. By geologists, it's called anorthosedic. It's a geological term for minerals and rock. And so these are the main differences. And this is where we're going to see most of the differences in terms of resources. And luckily, nature has given us a very good view of what could be of use on each one of the sides. And mostly is because we can see it every night, the near side. Let's take a look at iron. This is obviously a very important element on Earth. Everything is made out of iron and steel and all that. And if you look at it, high quantities of iron, up to 14%, are concentrated on the near side, on the mare. This came from the volcanic material. But look at the far side. There's not much there, but where is it mostly concentrated? On the place where China landed, on the South Pole Aitken Basin. So this is not only just a site that is important for scientific reasons, but it also, you can start seeing why it would be important to have metals on the far side of the moon. So it's an important one in terms of resources. If you look at titanium, same thing. It's mostly concentrated on the near side, the volcanic material. In fact, these places contains more titanium than you will find on Earth on similar regions. So it's highly, the moon has a high content of titanium. Now, the moon also has inside the near side and the far side, a very creepy side to it. But creep with a K, that stands for potassium, rare earth elements, and phosphorus. This is a region of the moon that when it was solidifying, the moon, after it was formed, and you will learn this through another lecture during the week, it was a liquid, and it started solidifying, and the last part that stayed as a liquid was this zone, in which you had heat-producing elements, like, for example, uranium and thorium. So you have radioactive materials there, you have rare earth elements, which are precious, we have potassium and phosphorus, which are important if you want at some point grow plants and anything that wants to grow. So this is a very important region, but again, it's concentrated on that side of the moon. Now that we know a little bit about the minerals and all that, on Earth, if you want to go after them, you're going to have to break the rock, and you have to dynamite and explode it and break it up into many pieces. This is another thing which nature has actually been good to us, because for billions of years, let me just show you one before that. This is the distribution of elements in the near side, and on the mare and the highland. As you can see, both of them have oxygen and silicon, but the highlands contain more aluminum and calcium, because this is the oldest material. You always will find aluminum and calcium in some of the oldest part of the solar system, and we will see that with asteroids. But on the mare, this is where you have the iron and you have the magnesium. So these are the two different concentrations that you find there. But as I was saying, what nature has done to us is that for billions of years, the moon has been bombarded by many asteroids and meteorites and micrometeorites. And what they have done is that they have impacted the bedrock of the moon, the hard part, and in the process, they have turned this hard rock into dust, pulverized the material. This very fine dust in the 60 to 70 micron size that is electrostatically charged, and that is already in the surface. It's ready for us to start working with it without having to use dynamite, because for billions of years, nature has done the work for us. And so what is that we find? This dust is what we call the lunar regolith. Somebody actually mentioned that at the beginning. Regolith is the very fine dust that you see on the surface of the moon and planet. Could be Martian regolith too. And this fine dust is what you see. Why is that we were able to leave some footprints on the moon? That's why we were able to do that. And it's mostly on the upper 10 meters, and they're mixed with the soil of the moon plus murated material is being turned and shone around, what's called gardening. It's like when you are in the garden, you're raking and you're mixing things. That's what happens on the surface of the moon. And it's made up of this very unique material that is very different from Earth. If you go to a river and you get very fine particles, or the sea, they're rounded because of our ocean and water. But the moon has never been exposed to water, has never been exposed to wind. And what you find is that this regolith is being shaped by impacts. And what you find on from very large particles, from the millimeter side all the way up to the micron side, is very angular agglutinates, these jagged edges. They're not rounded, they're very abrasive. This thing can eat up your systems. If it gets in your lungs, it's going to rip them apart. In fact, some of the astronauts were exposed to some of this, and they really felt that their lungs were burning because this thing was ripping inside. Not only that, they have been also bombarded by micrometeorites lately, and they formed these little dots. And even in the very tiny size of places, you can find this thing called nanophase iron. And this happens because the micrometer hits the rock, it melts it, it reacts with some of the hydrogen, and then it forms this iron that separates. So an important thing to take from this is that the regolith has been shaped by impacts, and this is the reason that we have it in the surface of the moon. Now, also the moon has been bombarded by billions of years by solar wind. These are particles that come from the sun every once in a while. They hit the moon, and because it doesn't have a magnetic field, then they're not trapped by the magnetic field like on Earth. On Earth, if you live in the upper latitude, you see the aurora borealis. I don't know if any of you live close to there, but you see these beautiful colors, and that's because the particles are trapped by the magnetic field. But here on the moon, it just gets implanted on the soil, and so the soil receives all this material. And this is important material. The solar wind implanted volatiles, you find things like hydrogen, like helium, like nitrogen, carbon that comes directly from the sun, and you can find it mixed with the lunar soil. And so it's important to know, because these things that you can pick up later, nitrogen and carbon are important, and it doesn't come from the moon. There's even this isotope of helium. An isotope is just a variance of an atom because it has an extra nutrient. It's called helium-3, but it's in a much more abundant than on Earth, even though it's a very small amount, parts per billion. ppb means parts per billion. That means one particle in a billion others. Very little, but it's been thought about that in the future, if fusion, not fission, nuclear fusion is controlled, which is something we have not done, they can use helium-3, and you can have power produced with non-radioactive byproducts. If you put helium, nothing that comes out from the reactor is radioactive, and that would be a good thing to have. So, but that's something in the future, if we can actually mine the helium-3. Then, these are found basically the finest grains. They're retained mostly by a mineral called ilmenite. Ilmenite retains these volatiles. And they're pretty constant. If you excavate 2 to 3 meters, you will find the same concentration, and then it's gone after that. So it's only at the surface. Good. I was talking about helium-3. I couldn't see it because this thing was blocking. So this is the helium-3 that I was talking about, and let me minimize it so I can see what I'm doing. And so that's the helium-3 that I was talking about in parts per billion. You didn't know what I was talking about, but here it is. All right. Let me go back. Now, of importance also is not just the material, it's the location. And there's this thing called the lava rills and tubes. And these are important because these are channels that were formed by volcanic material that flows through this. And these will be important because not only they're rich in resource, but these could be places where we could probably set up a habitation module. You can bring an inflatable habitat, you put it on these channels, and this is a way to protect yourself against the elements. This is called the rill. Interesting enough, when I was trying to see how to show you this, when I was in Luxembourg a couple of weeks ago, I was in my hotel room, I was looking at the ceiling and trying to figure out how am I going to explain that. And there in the ceiling of the Ibis Hotel in Luxembourg was the moon. I could see the moon in the ceiling, and I could see the rills right there. So it was incredible. I just had to take this picture because I could actually see the rills nicely formed on volcanic material. So these are the channels. But more important than the rills are the tubes. When lava flowed at some point to the moon, started going through there, and then the top solidified, the lava continued going and it left a tunnel, it left a tube. And so what we can see now is sometimes that tube, because of an impact, has been broken from the top. The crust has been broken, and we can see inside. These are very, very similar to what we have on Earth, the lava tube that we have on Earth. And in fact, on the right, you can see where the tube is going. It has been broken in several types on the top, but some of them are still intact. In fact, the European Space Agency is very interested on this because these could be places where we can have our first habitats, our first homes. Just like we did it when we were thousands of years ago, we started living in caves. Same thing is going to happen here. And so ESA has been looking lately for innovative ideas. So if you have some, you can apply. This is a lava tube on Earth. You can see in this on volcanic regions. And they were formed exactly like they were formed in the moon. So if you could live there, you can protect against micrometeorite, you can protect yourself against radiation. They're at a constant temperature. So these could be places where humans can actually live. So location is another important resource. How about water? Everywhere we go, humans, we're always looking for water. It's the basis of our survival. Is there any water on the moon? Or is there any possibility of having water on the moon?
Yes.
Oh, where?
On the polar caps.
Dark side of the moon.
On the poles.
Somebody said the far side of the moon. Well, it's interesting because here's what happens with the possibility. When we got there in 50 years ago, we didn't think there was going to be any water. And the reason is because the moon has this very interesting tilt with respect to the sun, with what's called the ecliptic. It's just 1.5 degrees. On Earth, we have 23 degrees, and that's why we have above the Arctic Circle, it's night during the whole winter time, and then it's day during the whole time. Here, the moon is fully illuminated constantly. If you go through a typical cycle, day and night on the moon, you will see that every single part of the moon is illuminated. And so there's no possibility, if any water falls in the surface in a vacuum, it will evaporate. It's even worse. The moon has this thing called libration, or precession. It wobbles. So what happens is that you can see the thing moving around, and even the north and the south pole is fully illuminated. So any possibility of water will disappear. There's no dark side on the moon that can be except from the sunlight. So there was no hope that water will be ever found. But then scientists started looking, well, what if, because of this inclination, how about if in the poles of the moon? If you leave the pole of the moon, either north or the south, if you're standing right here, you will always see the sun on the horizon, either a little bit above or below. So it's always going to be shining there. So what if these craters could be so deep that they have never seen the light of the sun? And what if water from comets, from ice from comets, or from asteroids have deposited there, and because it's very cold, they never evaporate? And so in the late 1990s, several missions were sent to verify if this could be something that could happen. So there was this mission called Clementine that had an instrument called radar reflectivity. Basically, it sends a radar signal, and if it bounces from a bright spot, if there was ice, it will tell you that it's different from some of the dark spots around it. And there were some very strong signals. So that was the first indication. Then there was the mission called Lunar Prospector. Has this very fancy name for an instrument called planetary nuclear spectroscopy. What this is that cosmic rays come from the universe, they hit the surface, and they get absorbed by various materials. And then a spacecraft can actually see which ones were absorbed. In this case, they saw the absorption of hydrogen. So they detected a large amount of hydrogen, not necessarily water, which is H2O, but hydrogen. So it wasn't an indication that possibly the hydrogen was coming from water. Then the Indians came with the Moon Mineralogy Mapper on Chandrayaan-1. This was the first mission that the Indians had run, and they were able to see that, in fact, with that spectrometer, they could see signals of water. And then came the Lunar Reconnaissance Orbiter. This is a mission that still is out there and that had other instruments, all of them confirming that there was probably water ice on these very deep craters. And so what these missions were able to accomplish is to find a couple of good resources. One, let me show you first. We're going to go around the North Pole during a typical days and night cycle, 28 days. And take a look at some of the craters as the sun goes around, and you will see that some of them, even though they're illuminated, sometimes they're going to have a dark spot. So here we go. So you can see, choose any crater you want. You will see that it's dark, and then the sun starts going around, illuminates some, but there's always these dark places. And these dark places is where it's very cold, and these are the places where ice can actually be. And you observe this on Mercury, you observe this on the Moon, and it's interesting to see this effect. And so, what these missions were able to find is, first of all, location. Location is a very important resource. That's why we live where we live on Earth, because we find a place that we can actually survive. And there were two important things. Yes, they found these permanently shallow regions. This is the South Pole, but the North Pole also has them. This is the places where we can find the resources. But as important, they found what was termed in the 1800s as the peaks of eternal light. These were named by a French Flammarion that called this in a very romantic way, places where light is always there. It is never dark. And indeed, very high places on the rims of these craters could always be light, about 95% of the time. So this is going to be important because this is a place where you can actually put a settlement or a base. And in fact, if you look at the plans by the Americans, the Russians, the Chinese, and everybody wants to put a base on the poles because this is a place where you can have light, communications, power. And not only that, at some point you can beam down that power down to the craters, and we will see later how that power can evaporate or sublimate the ice, and then you can collect the ice and turn it into hydrogen and oxygen and all the things that you want to do. So the rings of these craters are very important.
The what? Of the craters?
The rims, the outer rims. Okay, the top part, the edges. When you go up, there's this rim, this high part where you can actually set a base, and you will always be able to see the sun most of the time.
Sorry, just to be clear, so the Moon doesn't actually have polar ice caps?
No. And the reason is, first of all, it doesn't have an atmosphere, it's a vacuum. If you put a droplet of water like that, it's going to evaporate. I mean, it's just such a low pressure that it's going to evaporate. Very different from Mars, and we will see Mars in a moment. Okay. So, what these missions also did is that now we have a lot of information from remote sensing. These are instruments that can tell you from afar that you have certain materials. But nothing beats touching the soil. You want to go there and see and grab it in your hands and say, yes, I have water. It's not just a signal that I made things. So the first attempt to do what's called ground truth. Ground truth means you go and you dig and you verify that you have the resource. It was a mission that was going to be sent to touch the Moon. And so they looked at different craters and they found that Cabellos could be a good option. It has very strong signals of hydrogen and strong signals of water. And that's exactly what happened on a mission called L-Cross in 2009. What L-Cross did, L-Cross was a mission in which there was a rocket that was sent. And rockets, and we will see this in the class on propulsion, has different stages. You need all the fuel to get out from Earth, and then you spend that, and the second one to go into orbit, and then you leave the upper part. The upper stage is the one that's going to travel to the Moon. So the upper stage of that rocket, which was used to deploy another satellite, was used. They thought, well, why not using it, instead of just getting rid of it, to impact the surface of the Moon? And that's exactly what happened. So what they did is that they had these two spacecraft, the upper stage and this other one on the back. They separated so that the first one could go there, impact Cabellos, create a big plume, and then the second part had about 14 to 15 minutes to capture the data, send it back to Earth so we could see what was happening. And there you can see the little plume that came out. that detected for the first time in the soil the presence of water, anywhere from 3 to 8%. So this was a confirmation on the ground that water actually was available in these permanently shallow regions, or PSRs. So that was quite a discovery, but it's the only point that we have. In the future, as we saw on the last class in terms of how to, on Earth we go from resources to research, we need to probe around to see if it's how widely distributed it is, how deep it is, if it's water ice, if it's mixed with the soil. So we need to do more prospecting or more exploration. But this is the only data point that we have at this point. So what this has told us, and then last year came a paper that had compiled all the information from LCROSS and the Chandrayaan and Prospector, and has put some spots, those green spots are the places where they actually can think that there's exposed ice. Not only the ice is there, but it's exposed in the surface. And this is very important, because if it's exposed, you can just heat it up, and then this water can start coming out. And so what these missions, and it's important that it's, the reason why they're there is because how cold these places are. Let's take a look at the temperature on these places. This is a plot of the daytime on the left, and the the nighttime on the right. And here are the temperatures. It's hard to probably read the scale, but it goes from purples, 40 degree Kelvin, all the way up to 400 in the yellow. So look at the purple side. This is 40 degrees Kelvin, minus 230 degrees Celsius. It is so cold that the ice will stay there for millions of years. Okay, the moment it starts going around 110 degree Kelvin, it may start sublimating. Sublimation means you go from ice, from solid to gas, without even going to liquid. And so these are the places where you can find this very precious resource. And so the view that we have now is that if you look at any of the poles, let's look at the South Pole, even in the small amounts as compared to the area, about 3% of the South Pole is full of this water ice on these permanently shallow regions. So you can find these deposits that you can find there that could be useful to get water for human use, for propellant, for anything that you want to use, just like we do here on Earth. And the estimates right now range widely, but it's approximately around to 100 million to 1 billion tons of water per pole is the current estimate. That in terms of water on Earth, it's about, I forgot to check a lake near Luxembourg, but it's the size of a big lake, let's say, on Earth. It's not that much, but in terms of resources for propellants, you can fill up, a million of rockets. You can use it for humans to live there for the thousands. So there's a lot of water, and we will see later if that can be extracted when we look at the technology. So there was also water that was found on some other outside the poles, but in parts per million, that can be found there by a process called reduction. That means hydrogen of the solar winds reacts with the moon and forms this water. But also water is found by volcanic eruptions. At some point during the history of the moon, there were volcanic eruptions. These things came out, and small little particles trapped water on beads, very small beads. And so water is trapped in this material. And the important thing about it is that you can find it on more benign places to live, between 30 degrees south and 30 degrees north. These are the places in the equator where it's much nicer temperatures. And you can find these deposits up to 300 parts per million. I mean 300 parts of water per million others. So these are places where there's water, not on the poles, right on the surface. It's easy to get, but it just sometimes you're going to have to create your base close to this place.
So can I
So what's that?
I thought that, how can there be ice on the surface since the permanently shaded regions are only craters or holes created by lava movement?
Because the water is there, because it's not exposed, it's trapped in this glassy material. You have to crack the material, and then the water will come out. And the moment it's exposed, it will come out. So it's protected at this point. It's hollow particles. So that's what you have to get water. And the reason the water was formed is because it came from the mantle. When it was a volcanic material, water was coming out, and it was trapped. And that's why you find it.
So it's less accessible than the water found in permanently shaded regions.
Oh, in fact, that's a great question. Because look at what the only geologist, the only scientist on the moon, Harrison Schmitt, was able to see when he was walking around. He saw this orange soil, and that orange soil has water, and it's right there in the surface. You just have to heat it up, crack it, and water will come out. So the beauty of this is it's not in large amounts like ice, but it's easily accessible. So it's a trade-off. Later on, you will see if this is worth it or not. I mean, this is something you're going to have to do throughout the course. I'm not going to tell you right now what's better or not. That's going to be up to you.
When you said that water is trapped in the volcanic material, you mean that there has been water on the moon, on the surface, or into the moon? There has been water on the moon, for example, million years ago, or what's the source of the water?
All that water, if there wasn't water on the moon during its formation, it just went away. So it was completely dry by several billions of years ago. There was nothing left, unless it was trapped by this volcanic material. Maybe there's inside, if you were able to poke a hole and get some volcanic material, there may be something trapped inside, but it's really deep. It's not like a well that you can, drill a couple of meters and water will just come out. It's way down in the liquid part of the mantle, which is very little. So all the water that was at some point just went away. And the only one that has been captured is because it's in very cold spots on the poles or is trapped on this volcanic region. That's the only source of water. Okay? All right. So these are the resources from the moon.
One question. Is the moon still volcanically active?
No, it's not. Okay. It's at this point that's it. It's over. I mean, who knows? If it gets impacted by a big rock, it may crash the crust, and that will lead probably. But it's pretty much dead volcanically at this point.
Okay.
And that's what makes it different from Earth. Earth, you constantly has this volcanism, and you have tectonics, and it keeps changing the face of the Earth. But the moon has been kept the same way for billions of years, and that's why it's so scientifically important, because you're seeing the same thing that happened billions of years ago, and that's what makes it very unique. And you will learn that from one of the other classes this week. All right, let me move on now to other places where we can find resources. So let's travel to these amorphous rocks that one finds all over the solar system, the so-called asteroids. These are places, rocks, that are left over from the formation of the solar system. When the solar system was forming, it was just dust. And eventually started forming these rocks, and some of them became planets. Some of them actually just stayed as rocks. Some of them are as small as 1 meter, all the way up to about 1 kilometer in diameter, Ceres, which is it's an asteroid or a dwarf planet, you may say. And as you can see, what changes here is that they go from these very oddly shaped rocks to a rounded object. This is what's called differentiation, planetary differentiation. Let me explain what that is. At the very beginning of the solar system, you had just dust and particles that started just agglomerating. Very little gravity just kept them together. And they just started forming some of these rubble piles, they call it, just agglomeration of particles. As they started agglomerating more and more, gravity started going up, the pressure inside started going up, the temperature started going up, and to the point that you start melting the inside, and at some point that melting, it starts melting all the elements, and the heavy elements that are liquid start coming down to the center. And you differentiate between the hard, the heavy objects on the center, and the light ones that stay on the surface, to the point that you find something like on Earth. You have a core, then you have the mantle, the liquid part, and then the crust that, because it was exposed to the atmosphere, it cooled down. And so that's what makes a planet, this differentiation process, which most of the asteroids don't have. The asteroids are, most of the ones on the left, just a collection of rocks that never differentiated. So the same thing you find on the surface is the same on the inside. It's not like on Earth. And so that's something that it's important to understand, because that means that we don't have to dig deep to know what's inside, because we know that most of the asteroids are composed of the same material. And we learned in high school probably that these were concentrated on asteroid belt, a very well-defined band between Mars and Jupiter. But it's not like that. And at some point, they impacted each other, and they started moving around from their orbits to the point that you find these rocks everywhere. And if you look at night, you think, oh, it's beautiful out there, there's nothing. There's lots of rocks, it's just so small, but they're all over the place. And one that are very important to us are those ones that were trapped when they were moved from the asteroid belt. They were trapped on orbits very close to the one that the Earth has around the sun. You see there 3 different orbits. There's a purple, orange, and you see the blue one. The blue one is the Earth going around the sun. A lot of objects are trapped very close on these orbits. These are the so-called near-Earth objects. And you will see that these are important to us because we can access the asteroid and its resources without having to go all the way out to the asteroid belt. They're very close to us. Not as close to the moon, but closer to us. So these are going to be important near-Earth objects. And we know about them because we have used telescope from Earth to look at their spectra. Spectra is the light or the radiation that comes from them. And what this has been allowing us to do is to classify them. And there's classifications of 20 or 30 types. But let me tell you 3 important ones. Because most of them can be classified that way. There's the C type. It's called C because they have carbon, the carbonaceous type. Not only they have carbon, they have water. Up to 15 to 20% of water. And it's important because this is an important resource. This happens to be Matilda, which was visited in the 1990s by a mission called Near-Schumacher. So we were actually up and close. Then there are the S types, like Eros, that we also visited with the same mission. These are the silicaceous or stony types. Now you start seeing nickel and iron, and also some of the metals that one finds, the platinum group. And these are important because they have the important iron and nickel. In fact, some of the mining that we're doing on Earth is already asteroid mining because they fell on Earth, and there are some places that we can find very high concentrations of nickel and iron, and that's because asteroids fell on Earth, and that's why we're extracting them there. But if you really want to go after the metals, there's the M type. These are the metallic types, and here you find the noble metal, the gold, the silver, the platinum, iridium, rhodium. These are very unique elements because when a planet was forming and it started heating up, remember that the heavy elements go to the center. So they were able to concentrate the heavy elements, the iron and the nickel, and at some point the asteroid was hit by others and it left only the core. So the rest was gone and it never grew to be a planet. It was a baby that never made it actually to a human. And so it just retained the metallic type. And that's what you find on those types. They're extremely heavy, very dense, but they have their metallic types. If you have a hard time memorizing this, I'm going to give you a tip. CSM, Colorado School of Mines. So that's some subliminal advertising there, but that's the way we always think about this. Now, how do we know also about them? Well, we know because we have more than 55,000 meteorites that have fallen to Earth. We already can hold them in our hands, and we can see them. And we classify them very, very similar to asteroids. We have the stony types, which is close to the carbonaceous ones, the stony irons, a combination of both, or the iron types. And actually, let me show you some of them. So let me get out of here for a moment. Stop sharing. I need to concentrate. Stop sharing. All right, I'm going to show you a few of those. First, where am I? Oh God, I don't see myself. Okay, well, hopefully it will be fine. What I have in my hand is a metallic type. So hopefully you can see. I don't know if it's going to focus nicely. This is some of the heaviest elements that you can hold in your hand. This is nickel. This is iron. This comes from the core of an asteroid that later on fell to Earth. And so these are very heavy materials that are very similar to the metallic asteroids. Extremely heavy. And so these are the types. Then there are other ones that may look like nothing to you. Just a rock. A simple rock. This, what I have in my hand, my fellow students, is the oldest object that you can hold in your hand. This thing is 4.5 billion years old. This is the oldest meteorite that has fallen into Earth. It just happened to fall very close to the place where I was born, in Mexico. And it's a very famous meteorite called Allende, 1969. It impacted the town, and I remember my uncles and saying, hey, we heard this big thing. And everybody went out and say, oh, there's rocks. Well, the next day, the whole scientists from all over the world descended, and they called this in, and they had this meteorite as the oldest material. You can see interesting things about it. I don't know if you can focus. The dark part is the crust. This is when an asteroid goes through the atmosphere and burns, forms this crust that is somehow burn material. But then inside you see these white speckles. These white things are aluminum and calcium. Aluminum and calcium have a very high melting point. So these are the first metals that became from vapor to solid on the solar system. The first metals that were formed. So this is an incredible rock. It's the oldest one that you can find, and it's part of the formation of the solar system. So we have those things on Earth, and that's how we learn about asteroids. But at some point it will be important to go there and find out more about it. I got a little bit carried away because this thing really excites me. But let me share again my screen, and let's go through this. So this is what we know about asteroids. All right. Comets are also important. Comets have ices, have water, have methane, have ammonia. And the interesting thing about comets is that they still are expelling this material. That's why you see their tails. In fact, some asteroids are extinct comets.
We can't see the screen.
Oh, you don't see the screen. I'm sorry. Sharing. You don't see it?
Not yet.
Ooh, what's going on? Stop sharing. Let me share. Share. Microsoft. Share. See it now?
No.
What did I do? Oh no. Let me see. Stop sharing. So what you see now? You see the screen. And so let me see this.
What's up?
Share. It says share. You gotta see it now.
No, I can see it. I can see it, but for any kind of reason, here it's not sure.
You see the comments here. No. This is cool. Let me see. Stop sharing. You're sharing Microsoft. Let me see. Let me try again. Let me share.
We can see but he didn't see us, I think.
No, you see.
Only can see the teacher.
Do you see anything now?
No.
Great.
No. What did I do? That's why I shouldn't pull out like this. Let me see. Stop sharing. Let me
Just start the session once again.
What can I do? See each other, right? Okay.
Take a picture.
Is my
Was that okay?
No.
do it.
Try now to share.
Oh,
No, yeah.
Now I see.
see it?
Yeah.
Yes,
Yeah.
it.
You see your desktop.
Desktop, exactly.
Stop. Just one more thing. Stop sharing. Let me go to my PowerPoint. Let me skip it. Okay. What are you laughing about?
Now we see you.
What's up?
That. You erase the desktop probably that is full of things, but let me see.
Why don't we rely on Miguel's laptop?
How about that?
One second. Wait. Now should.
It's visible there. Why don't we just put that at the head of the table? Look at that.
Almost done actually. So
Don't touch anything. I think I have to change something here.
I think we will like him.
thing.
disconnect because I'm recording.
Is this going to be in the recording too?
Probably yes.
Why don't we just take the laptop and put it over there?
Stop sharing. So now, what do you see? You see me and something else on the side?
Yeah. We go and
Yeah.
Do it again, one more time. If it doesn't work, you just have to watch the screen. Microsoft Power, share. And don't see the comments there, right? Do you see it in yours?
No, wait. This one was working before.
You see the comments in your screen, in your computer, Miguel?
I see it, but it is second screen that is not showing the right thing. It's,
Somebody's telling me here that can see it, actually. Usta, he's saying he can see it in the chat.
He can, yeah, he can.
it's cheating.
He's the privileged guy, so everybody's going to have to leave now, go somewhere else. Yes, but let me see.
Now we see ourselves.
Yeah. We can see ourselves.
Would it be possible to connect your screen to the right monitor?
Hey, how, I actually
Do you know
didn't
this-
see
do you know this
stuff.
name, yeah?
You there? How are you?
Everything.
Do you see him? Yeah, okay, here's it.
Okay.
Okay. Let's see.
Share it?
Let me share.
Yeah.
Microsoft PowerPoint share. About now. Do you guys have to go?
Yes.
There?
What
Okay. It looked like from outer space there, but do you see the comments?
You.
You do?
Yeah, we see comments.
Yeah, it's okay.
It's comments.
Right. Okay. All right, let's keep going then. So I mentioned that the Rosetta mission from the European Space Agency was actually able to visit a comet. This was an incredible mission. And what you see here is that the interesting thing about comets is that you don't have to actually not even heat them up. I mean, the resources are coming out of this thing. Water, ammonia, methane, you can just collect them. The problem is that there are very few of those that we can access. They have very strange elliptical orbits, so we may be able to see it for a little moment and then they're gone. So the mission will have to synchronize, get there, extract the resource, and let it go. So this is hard. That's why asteroids are more important. But something to consider, comets. So let's keep going. And now, so we can add now to the mix of things. We got the moon, we also have the asteroids. But let's keep going now to our load of resources, that Mars. Mars, that is our nearest planet. And Mars that has a bunch of resources. First of all, the reason we know that we have had several missions going around, so we know a lot from remote sensing. We also have landers, all sorts of rovers on the equator, also in the upper latitudes. So we know a lot about Mars in terms of these resources. And what we know is that they have all the metals and the non-metals that the moon has. But more importantly, you can even see it, is the water on Mars. Take a look at the water on Mars. You can even see it on the pole. It's right there in South Pole and the North Pole. Mixed with carbon dioxide, but it's right there. So it has plenty of water. And we have even gone there with a mission. The Phoenix lander landed on about 68 degrees north. And what it found, it just scraped the surface, and just a few centimeters you could find water ice. You can see 4 different days. I think it's Sol is the day of the Mars. It's like a day here. So you can see how it started actually evaporating. At some point it was gone. So the moment you expose the water, just like on the moon, it will actually start evaporating. But it is a few centimeters. But you can also find it closer to, and this is hard because humans are not going to live in the poles. This is very harsh environment, very cold. So what about other latitudes? For example, between 50 south and north, which is some of the places that some of the agencies and companies are trying to go. Here at 50 degrees north, you can find subsurface ice just 2 meters below. These are glaciers that have been covered by dust, but if you drill 2 meters, you can find the ice. And it's 90% pure water, so this is very, very important. Now, if this is too high up, and you want to go even more to the equator, you can find water on what's called hydrated minerals. I have a couple of here. Hydrated minerals that contain from 4 to 20% of water. For example, you have gypsum. So gypsum contains up to 20% water. If you heat it up to 150 degrees Celsius, water is going to start coming out. There's also clays, like cementite. Any clays that you find, they hold water, and those things also, you heat them up a little bit higher, by 400 degrees, and the water will come out. And if you're really desperate, and you cannot find water anywhere, water is everywhere on the regolith, but in very small amounts, 1 to 2%, and you have to heat it up real high, about 700 degrees, but water is trapped on the minerals, just like it's trapped in the asteroids. So these are the hydrated minerals. They're full of water. And so water is everywhere. But not only that, Mars is unique because it has an atmosphere, very thin, about 0.6% of the Earth. So the pressure is very low, but 96% of that is carbon dioxide. And the moment you have carbon, you have methane, you have hydrocarbons, you have plastics, anything that you want to create out of carbon, just like we do here on Earth. So that's one important thing about Mars that is not on the moon or asteroids. Its content of carbon dioxide. And let's not forget about the moons of Mars. Very important. Phobos and Deimos, which are most probably trapped asteroids. These are asteroids that, when moving around, were trapped by the gravity of Mars, and they may be very close to the type Cs. They have water. And so these are places that one can access more easily because they have low gravity, and you can use it as a base before you actually get to Mars. And we will talk about that later, and you will hear more in all your lectures this week. So here you are with all of your different elements, the moon, Mars, asteroids, even space junk, space debris that I put there as a resource. The question is, which space resource is more valuable? And I'm not going to tell you that. You are the ones that are going to tell me this somewhere around the course as you start seeing not just the quantities, but do we have the technology to extract it? And is there a demand by this? Is there a customer? And you're going to be learning about this during the entire course. And at the end, you will figure out, you'll be able to tell and decide which resource you think is more valuable and what we should go after in the near term or in the long term. So that tells you a little bit about resources beyond Earth and what I have tried to do. And I'm going to pull out now from this. I'll just leave it there. What I tried to do was to give you an overview of the resources in the near term. Again, I'm not focusing on things like Europa that has a subsurface ocean, or Titan, the moon of Saturn that has hydrocarbons just too far away in the future. These are things that can happen in your lifetime, places that we can go and we can concentrate. And so what's going to happen during this week, if we can make Canvas work today, you go there and you will find a variety of lectures. There's going to be one lecture that is about 15 minutes long on just the solar system, how the solar system was formed, the different planets, so you understand the whole point of view. Then you're going to find a lecture about 20 minutes or so, 17 minutes about the moon. This was by Paul Spudis, one of the main advocates of resources on the moon. He died last year. He was able to record this lecture, and you will see how he advocates for the moon. Then you're going to hear from the world experts on asteroids, Dr. John Lewis, who wrote the books on asteroids, and why he thinks that's an important resource. Then you're going to hear from a Martian, or not a Martian, but a scientist that likes Mars, and he concentrates on basically water on Mars. And you're going to also be hearing about planetary geology, planetary geophysics, so that by the end of the week you can have an idea of different opinions. Then I'm going to ask you to comment on a discussion board on some of the questions that I'm going to raise. You can pick two. You may pick and comment on that, or pick on another one, the asteroids. And that is going to be due, hopefully everything's working, by Saturday night. The moment you post your comments, then you're going to start seeing the rest. and you're going to be asked to comment on others. If somebody commented on other things, you may say, I don't think so, I think you're crazy, or you think you're right, or I agree with you, or something that you want to comment. And so I'm going to ask you to do that as part of the, besides watching the lectures, I want you to comment on this. The other thing I want you to do, if it's possible, is to, something that we talked about, just a recording of about 2 to 3 minutes of yourself. And all these instructions are going to be there, how you can record. You click there, and it's going to start recording. It's going to tell me where you're from, what it is that you studied, what are your interests in space and space resources. All the questions are going to be there, so it's going to be very specific. I'm just going to have that as a record when I start forming the teams. So, and finally, you're going to pick the news of the week. And that one, I just want you to pick it and put it on a board and say, this is a link, and I think it's good for this, and then we'll comment on every class. We're going to be talking about this. Today, I went a little bit heavy on material because you don't have access to videos, but once you start having videos, we're going to dedicate these Monday sessions to just questions and discuss things among ourselves, and you can also, I can also learn from you. So that's what's going to be happening. I'm going to be looking very closely to see if this thing has opened for you, and I'll try really hard so that you can see it. But let me know if you have any problems. Okay? Any questions so far?
I've got one relating to asteroids. I've read some news stories about asteroids made entirely out of diamond. But since diamond is crystallized carbon that was created after millions of years of intense pressure, how can isolated pieces of diamond exist as asteroids? Shouldn't they only exist as part of deeper layers of asteroids?
No, unfortunately, those are things that, and that's why I want you to check the news. And I'm going to have a place there where he talks about reputable resources. People get carried away because they think it's carbon, there's this big diamond. Necessarily, they may be some things that are carbon, but carbon comes in different shapes. Carbon can be formed in different ways, but you will not find actually diamond. That requires that you say it's a lot of pressure. This thing is just barely, don't have any gravity. And you don't land on an asteroid, you dodge because there's no gravity. And so you're right, I mean, that doesn't happen.
Yeah. Alright, thanks.
Okay, any other question?
The assignment, are they clearly written out on canvas? So we can look up?
Oh, it's all going to be there very clearly. You're going to do this. In fact, you're also going to see the schedule of what's going to happen every week, all the assignments, the rubrics for every assignment, how much I assign for points, so you can see exactly how much you're putting in every effort. So everything's, it's needs to open. So I'm going to try all day long to bother these people until I get it right.
Okay, thanks.
Sorry, for the next week, do you think me and Farzana could also have access to the website?
Yeah, I want to talk to you girls after this is all over. So give you access to all that. So let me see. Any other questions at this point?
It's okay.
All right. So hopefully you learned something about resources today. It's a fascinating world out there. It's unbelievable what we can learn about the solar system and resources. But this is the first part. This is the science. Now we're going to get a little bit more into technology and customers and business and legal issues, which is a whole different world. But you need to understand everything as a whole because that's what is required for this field. All right?
Thank you.
Thank you.
I'll see you.
Thank you.
Next year.
Way to go.
It was great to see you.
Yes.
Are you guys hanging on to chat?
Any questions from me?
No, I just...
Who's the pen?
It's Michelle.
Michelle. Let me say something.
Oh, yes. I need one to explain. We'll see you in the morning.
Yeah.